You see it literally every single day. It's under our feet, it's in our walls, it's the very backbone of our cities. But really, how often do we stop and think about concrete? Well, today, we're going to pull back the curtain and uncover the incredible science packed into this everyday material, starting with its most humble ingredient.
So let me ask you this. Right after water, the stuff we need to live, what is the one natural resource that we humans consume more than anything else? It's not oil, it's not wood. The answer is probably not what you're thinking. Any ideas? Here's a clue. Our entire modern world is literally built out of it. Yep, it's sand. Just simple, everyday sand. At the end of the day, it's just tiny little broken down pieces of rock, usually silica or quartz. And this super common material is, without a doubt, the foundation of everything we build.
Okay, so why is this grainy stuff such a big deal? Well, it goes way beyond the beach. It's the key ingredient, the real heavy lifter that gives our most essential building materials all of their substance and strength.
I mean, think about it. Sand provides the bulk and the muscle in concrete and asphalt. It's totally essential for making glass, for making sandpaper, even the mortar that's holding bricks together. Take it away and our entire infrastructure just crumbles. It wouldn't exist as we know it.
So, we obviously need sand. But here's the catch, and it's a big one. You can't just scoop up any old sand and start building. Nope. Engineers have to be incredibly picky, because getting the right kind of sand is absolutely job number one. And the difference is like night and day. See, engineers, they love river sand. Its particles are all sharp and angular, and that means they can lock together really tightly and form a super strong bond. Sea sand, on the other hand, it's a total disaster for concrete. The grains are too smooth, they don't grip, and even worse, they're loaded with salt. That salt literally sucks moisture out of the air, causing dampness and corrosion that can just rot a structure from the inside out. So, how do you sort all this stuff out? Well, engineers use this surprisingly simple but really effective method called sieve analysis. Honestly, it's basically a stack of kitchen strainers with different sized holes. You pour your sand and gravel in the top, you give the whole thing a good shake, and all the particles get sorted by size. It's kind of like a coin sorter, but for rock. And what you're aiming for is something called a well-graded mix. See, you don't want all your particles to be the same size. The best way to think about it is like a jar of jelly beans. If you only have huge jelly beans, you've got all these big gaps between them, right? But if you pour in smaller ones, they fill in all those empty spaces. It's the same idea in concrete. This mix of sizes gets rid of empty space, which gives you a denser, stronger material that needs way less of that expensive cement paste to fill the voids.
All right, so we've got our ingredients sorted. Now it's time to talk about the recipe. And I'm not kidding when I say making concrete is a lot like baking a cake. It's a precise chemical process. You can't just eyeball it. Every single ingredient and its exact proportion is totally critical. At its heart, though, the recipe is pretty straightforward. You've got your aggregates, that's the sand and stone we just carefully sorted, and they act as the filler. Then you have cement, which is basically the superglue that binds everything together. And finally, you have water. That's the activator that kicks off the whole chemical reaction that makes it hard. Now, if you only remember one thing from all of this, let it be this. The single most important thing that determines how strong concrete will be is not how much water you add. It's the ratio of water to cement. This is like the fundamental law in the world of concrete. It works like this. A high water to cement ratio, so a wetter, sloppier mix, is going to give you weaker concrete. A lower ratio gives you much, much stronger concrete. It might seem a little backwards, but using less water creates a denser cement paste. There are fewer tiny little pores inside, which means there are fewer places for cracks to start. Simple as that. So you followed the recipe perfectly, but how do you actually know if you've made something that can hold up a bridge or a skyscraper? Well, you have to test it. And not just for its raw strength, but for its ability to survive for decades out in the real messy world. Check this number out. It's pretty fascinating. Concrete's tensile strength, that's its ability to resist being pulled apart, is only about 7 to 10% of its compressive strength, which is its ability to resist being squeezed. That's why concrete is an absolute beast when you compress it, but it'll crack pretty easily if you try to bend or stretch it. And that compressive strength, that's the gold standard for measuring concrete quality. In labs all over the globe, engineers make these little cylinders of concrete, let them cure, and then they literally crush them with these massive hydraulic presses just to see how much force it takes for them to fail. But here's the kicker.
A building can be incredibly strong on the day it's built and still totally fall apart over time. Strength means nothing without durability. That concrete has to be tough enough to fight off constant attacks from the environment year after year. And trust me, there are a lot of enemies out there. You've got sulfates in the soil that can seep in and actually cause the concrete to expand and crack. You've got the simple cycle of water freezing and thawing, which can make the surface just flake right off. You can even have a destructive chemical reaction happen between the wrong kind of aggregate and the cement itself. But for every problem, engineers have come up with a clever solution, from special cements to fancy chemical additives. And this all leads us to the final and maybe most important concept, where all this science comes together. It's called mix design, and you can think of it as the master blueprint for making the absolute perfect concrete for any specific job. Mix design is basically the final custom recipe. It's where an engineer takes absolutely everything into account: the strength you need, the local weather, the kind of sand you can get, even the budget, and they create a precise formula to hit all those targets. And here's the big takeaway from all this: there is no such thing as a one-size-fits-all concrete. It just doesn't exist. The mix that's used for your sidewalk is completely different from the high-tech mix used for a massive dam or a nuclear power plant. Every single one has its own unique, custom-designed recipe. And that kind of leaves us with one last, pretty big question. We've seen just how picky engineers need to be, especially about something as simple as sand. Our entire civilization is built on these incredibly precise recipes. So what happens if those specific high-quality ingredients, like that sharp, angular river sand, start to run out? It's a huge problem that engineers and environmentalists are dealing with right now, and the answer is going to shape the world that we build tomorrow.